Yep, there we go. Okay, welcome back, everyone. So we're going to dig into part 2, but of course we didn't finish last week's presentation, so wasn't a whole lot of questions. So I do want to finish up about grouping, but let me make a quick announcement. So it might have been Diana that you pointed out, and I apologize. The proposal template, I had fixed it, but it turns out I fixed the document, but didn't fix the link. So it kept pointing to an older version. And so I felt kind of silly. So there was originally in the independent variable, it said one quantitative, one qualitative. That was an old version. So if you're doing sort of a null hypothesis test, you may only have one independent variable. So the template didn't match the direction. So I apologize for that. That should be fixed. If there was an issue, I did not. I will start grading the proposals tomorrow and Friday. So hopefully I can get those back to you soon. And then the other thing I want to point out is there's this link is now live, and I'll throw it in the chat so you have it now. So we have 4 time slots. We'll see if these, if we're trying to, let's keep it to 8. So don't add rows because we would like to keep the sessions to about an hour and a half, just to recap the way. So we have 2 during the day and 2 in the evening, and fingers crossed that maybe some of you can do during the day. If that, I know that is probably not possible for a lot of you, but if the 2 evening ones get filled up, we can add another evening one if need be. But we want to keep this to 8. So the way the sessions are going to work is you're going to give no more than a 10-minute presentation during that block. And then you'll watch your peers give their presentation. We'll have a peer feedback form, so you can give anonymous feedback to your peers. And also I think it's really valuable to see what other students are doing, but we don't have time for everybody to see everybody else's. That would take too much class time. So this has worked out quite well, kept it manageable to under 90 minutes, sort of as an additional time to get together. So just put your name in a slot. And like I said, we'll keep an eye out. If we see the 2 evening slots fill up, then we can add move one of the daytimes to an evening. But we thought we'd start here. Questions about this? Okay, great. So that, again, that link is also on the project page.
One more thing to note is that the reason we want as many people in one time slot as possible is you're going to be giving peer feedback to each other. And so the more people there are, the better, right? Because then each of you will get 7 other your peers feedback.
Mm-hmm. It makes the anonymous more anonymous. If you're only in there with one other person, you
Right.
clearly know who, so we'll try, if that, one of the sessions is really light, we'll try to shuffle. So the sooner you can sign up, the better. That would be very helpful. All right. So just recall last week we were looking at SAT scores, I think predicting verbal math scores from verbal scores. And okay, where are we? So, okay, right, that's where we left off. And so we kind of had a pretty decent model. What was our R squared at the end? We had an R squared of 46.8, or about 47%. We want to kind of consider, and we'll talk about this in much more detail next week when we talk about multiple regression, but even in bivariate regression, we want to start paying attention to sort of the implications of grouping variables. And so the first thing, as always, before you do any analysis, you generally want to look at your data as best you can. And so here, I've just taken the scatter plot and created 2 different point types and colors based upon the sex of the individual response. And so we want to know, now, of course, being an educational researcher, I know sex is very frequently, kind of an indicator of differences in various ways, or correlate. So, of course, it's something I would want to explore. In your particular field, you might know of what grouping variables. Sometimes you're unsure. So this one might be a little less clear, but if you look at this long enough, you might notice that, well, the red triangles, if I were to group them, kind of fall here. And then the blue circles, I'm sorry. I might say they're kind of clusters. It might be a little bit of separation. Of course, there's some overlap here, but I have a lot of red triangles down here without blue circles, and I have a lot of blue circles without red triangles here. So let's just explore what's going on. And so we can look at this in terms of a residual plot. Now, here I have on the side, these are rug plots. So that's just a way of kind of looking at the distribution. This gives me another little indication that maybe something's going on, like this blue one is shifted up a little bit more. Certainly the histogram, I think, starts to reveal. We'll deal with this guy over here, this person over here. But if I look at the, females, the center of the histogram to my eye looks a little bit less than 0, and to males is a little bit larger than 0. So this is in the residuals. So those are things we might want to take care of. So let's, one way we can do this is we're just going to separate these out into 2 data frames. Okay. And like last week, I'm going to calculate my descriptives, and we see the means are actually quite a bit different for, well, I'm sorry, the verbal, on the verbal score, there's about a 12-point difference, but on the math scores, there's about, a 28% or 28-point difference. So, so we could just run this as 2 separate linear regressions, right? And then here we could see the intercepts are quite different. And even the slopes are, different by almost 0.11. So, so we see that there's something going on here, right? And if we plot it, right? So this red line here in the middle is sort of the overall regression line that we estimated last week, and this kind of thicker red line and this thicker blue line are for females and males respectively. The vertical lines are the means in each one. So we could see on average females score better than men or males on the verbal, and males score on average higher than females on math. So is a common phenomena, unfortunately, in both cases in education. And so we kind of see that play out here. So why would we want to do this? Well, if you remember, so here we go. I was looking for this. The R squared, right, which is sort of our measure for model fit here in our regression models, is almost 47%. Now, if I look at the R squared for the model where I only considered males, well, I get 47%. It's a marginally, like not even a full percentage better. But when I look at the females, I'm up to 51%. So the 2 R squareds are better than the single model, right? And so that's why, right, we can kind of model this better. So this is, we could do it this way. What we'll see next week when we talk about multiple regression is how can we include this grouping variable kind of in one single model to kind of estimate it together. But sometimes you may want to separate it out. And here, I just trying to show a little bit of like the implications of kind of hidden confounders. In this case, we have sex as a variable, but a lot of times we have these other variables that are kind of around. Sorry, my dog wants to leave the room. All right, so there we go. That's the summary. The other thing I want to talk a little bit about is outliers, right? And so here's the residual histogram again, and we have this kind of point out here that kind of falls far away, and I highlighted it. So the residual is larger than 200. I did that just to make it look red. So what is the impact of that one observation, right? We want to take a look at. And well, let's look at it in the scatter plot, right? So here's our regression. So it's this point right here, right? It makes sense, right? If the residual is the distance from here to the regression line, and that's clearly a line that falls really far away. If we were to draw, kind of an oval or a box around these points, right, that clearly falls out. And what we see is it's a female who got a 490 on the verbal, but got a perfect score on the math, right? So not only, right, so there's a ceiling effect here, right? Remember, I think the 800 is the highest score you can get on each subject matter test, right? And so that's kind of having implications. So let's see what happens here. So here's our regression output on the left. And on the right-hand side, what I've done is estimate the regression removing that one observation. So I'm just keep looking at the ones that have a residual less than 200, right? So that just eliminates that one. So we see the intercepts are different, and the slopes are not terribly different, right? But this is where things get interesting, right? So our R squared was 46.9%. And just by eliminating one observation, we've increased our R squared to over 50%, right? So that's an over 3 percentage point difference. And so this is something really, really important to consider, the implication of outliers. And I'm not suggesting that you necessarily always delete outliers as we did here, but you definitely need to examine them and see what the implications or how they're impacting your model fit. And you could do sort of some rescaling to kind of get things in there. So you could do a log transformation. That's one way to bring in outliers, particularly in a positively skewed distribution. So I got a couple of more examples. So here I'm going to artificially add in some other outliers. In this case, I'm going to assume somebody has a verbal score of 1200 and a math score of 1150. And so I'm just kind of adding that to the SAT. I need to reverse these slides, right? And this is where the point is. Now I'm estimating the regression lines here, and you can see they're not terribly different in terms of intercept and slope, right? But where things get kind of crazy is I've taken my 46.9% R squared and now raised it up to 54.4. So not only is it an outlier, it's, we tend to refer to these points as having leverage on our model. So in this case, the outlier is actually beneficial from the point of view of model fit, but again, not really appropriate. So let's look at another one where we're going to look at a verbal score of 300 and a math score of 1150. You could see the intercept changes dramatically here, as does the slope. This is where I put the point over here. And so you can kind of see how, the red line is our original regression line. This gray line is the regression line adding this outlier point. And right, remember what we're trying to do is minimize the sums of squared residuals. So that's creating a very big, if I take that distance and square it, creating a very big rectangle, right? And so it's contributing so much to the model that it's really kind of, you can almost vision it pushing that regression line up to try to reduce the area of the squared residual as much as possible while balancing the rest, right? And so these are kind of the roles. Now, this is where we can start talking about, right? And here's the R squared. You can really see the impact here, where we've gone from the 47% all the way down to 27%, right? Adding one observation can do that. And so you need to be really, really careful. And so one thing we should say here, like one of the major assumptions that we have here that we've talked about in the null hypothesis test, but really haven't brought up yet, like regression and a lot of what we've talked about fall into these class of models that are called parametric models. And we're using the frequentist approach. The frequentist approach to hypothesis testing or to inference is that there is this sampling distribution that follows a normal distribution. For regression models and similar models like this under these parametric have this notion of, or have this assumption of normality. And I want to make this clear because a lot of people get confused, and I want you to check. Often if your individual indicator variables are normal, you're okay. But the normality assumption is that the residuals are normal, right? And so if we go back and look at, say, this one, right? This is pretty close, right? The residuals are pretty closely normal, with the exception of that outlier, right? That is going to create a little bit of skewness, right? So the combination of outliers and skewness in your residuals could cause violations of the model and kind of can cause problems. So we're going to look at another example that I actually, did a little bit on many years ago, kind of kind of close to my research area at the time. And this was looking at in New York State. Here, I'm going to look at grade 8 math scores, but we'll break it out, or I could show other grades and other subjects in a minute at the end. But from 2012 to 2013 was a big year in terms of the New York State assessments, because 2013 was the first year that the assessments were aligned with the Common Core standards. So if you're not familiar, Common Core standards was a sort of a national initiative to kind of realign or kind of standardize curriculum kind of across the country. It's, not without controversy, but that's kind of where we currently are. And just so you also know, so New York State gives these national gives assessments to all students in the state in grades 3 through 8 in math and ELA. And then science is, I think, also given in grade 8. But we're just going to look at ELA and math and focusing on math in the slides, and then I'll look at the others in a moment. So this was a big deal, and it made a lot of press because when you looked at the scores at 2013 compared to 2012, they look like they dropped dramatically. I mean, they did drop dramatically. And so there are a lot of questions that came out of this. I did some research on charter schools, and so I was interested in how these changes, were the changes the same for both charter schools and traditional public schools, and was the drop in a predictable fashion? Because if you realign the assessment without realigning the curriculum, that can be problematic, and it may not actually be that there's less learning. It's just you're assessing things that were, not connected to the curriculum. So what's great is New York State makes all this data publicly available, at least at the school level. So you could go look up New York State report card and go download databases of it. They're all in Microsoft Access, which you can actually read in R, thankfully, because there's no version of Access for Macs, but there are tools to do that. So, but I've pre-processed some of this data into a data frame called report card. And this is kind of what the data looks like. As you can see here, these are the first 3 rows. These happen to be schools in Albany. In fact, I have one kid that is actually currently attending this particular school, William Hackett Middle School. Just coincidence. We could scroll through and see other schools, but of course, Albany's at the top because that's where it falls alphabetically. A couple of things we're looking at. So we have number of tested in 2012. We have a mean score in 2012 and a passing rate, the percent of students in that school that passed, and then a charter school indicator. So that's true for 2012. And then I have them also for 2013. And it's not scrolling on me for me this year, but and we can see this is grade 7 math, and we have a whole bunch of grades and subjects. Just real quick, these assessments are scored on a 1 through 4 rubric. And in New York State, getting a 3 or 4. So when students get their score, they get a 1, 2, 3, or 4. A 3 or a 4 is considered proficient. Okay. And so we'll see that the passing rate is the percent of students in that school that got a 3 or a 4. But I think I'm going to start with the mean scores. I'm going to look at passing, right? Because that's kind of what the newspaper has looked at. So we can see here overall, right, 60 in 2012, the median passing rate for schools was 65%. And in 2013, it dropped to 20%. So you can imagine politicians went crazy. The public went crazy. Here's the distribution of the scores, the passing rate. So here I'm looking at schools, not individual students. I want to make that clear. But from a statistics and modeling point of view, I immediately I see one significant problem and one less significant problem. If I look at the distribution here, it's not quite normal. It's a little skewed. So that worries me a little bit. Passing rate for 2013 worries me a little bit more, right? And again, the models really presume normality in the residuals, but I know in this case in a bivariate regression, if I have skewness, non-normality in my independent or dependent variables, it's likely my residuals are also not going to be normally distributed. So the first thing I'm going to want to do is I'm going to try a log transformation because I have a right skewed, okay? And so that's what I'm doing here is I'm taking the log of, well, I have to do this little trick. I'm actually taking the log of the passing rate plus 1 because log of 0 is undefined. So I can just add 1. That there's nothing wrong because it's an equal. I'm adding 1 to everything. So now this is what the distribution, it's better. I have this big bump here at 0, again, because I have a floor effect, right? I can't have anything less than 0%. So this is often a phenomena that happens when you have bounded measurements. But you're going to see kind of, because this is kind of a messy data set in some ways, and you'll see how I often tackle these things. So what the strategy I use is I'm going to, train some models using both the raw metric and the log transformation. And see how different my results are. The reason why is I would like to use the non-log transformations because it's easier to interpret. When I do the log transformation, now I have to take anti-logs to interpret kind of coefficients and things like that. So that's kind of how I'm going to proceed. So of course, I'm also going to look at a scatter plot. And now we have yet another problem here is that on the surface, this doesn't really look linear, right? And I'll show you how I'll tackle that in a few minutes. But the log transformation, again, is a little bit better. Again, if you exclude these points like this bottom row where we have a lot of schools that scored at 0, if we exclude those, right, I can probably get a good line, but man, there's this 0 is really a bit of a problem. Okay. So the first thing, let's just look at the correlation. So correlation using the raw metric, right, the passing rate is 0.78 or 79 if you round it. In education, that correlation is huge, very, very large. So this is to say, at least the relative performance of the schools didn't really change from 2012 to 2013, right? Because we could predict probably the correlation suggests we're going to probably very with a fair level of accuracy be able to predict 2013 scores by just knowing the 2012 scores. If we look at the log transformation, which tries to get our assumptions a little bit better in line, the correlation is actually 0.83, right? So 0.79, actually 0.84 if you round it. So the correlation is a little bit better, the log transformation. Now, in terms of write-ups, right, again, the non-log transformation is a little bit easier to interpret. So when I wrote this up as a blog post years ago, I used the non-log transformation, realizing that I'm using a more conservative estimate, right? I could have picked the log so I could have report a higher correlation, but for the simplicity of reporting. So I'm just trying to point these out as like a lot of little decisions you need to make as you do your modeling, because your assumptions are, it's rare that your assumptions are going to fit all the time. Something's going to be a problem. And I think the principle you need to have is transparency. So if you're going to make decisions along the way, just detail what those decisions are and why you made those decisions. And if you start conducting research in a reproducible format, like in the labs, right, you're doing these in R Markdown files, you can always go back, reopen the R Markdown file and run your analysis, get the same result. You could share it with someone else. They can make slight tweaks in the decisions along the way and, see how the results differ. Okay. So let's do the linear regression. So here we're predicting 2013 from 2012. And we can see, so we have a slope, we have an intercept, but I'm going to just go right down. So the R squared is 62%. Again, that's pretty good. That's a lot of variance accounted for having only one indicator variable. If I use the log of passing in 2013, right, you should expect the R squared to go larger because we already looked at the correlation. So we have like 70% if we use the log transformation. All very good. Okay. So that's just predicting 2013. Now, what I had indicated at the outset is one of my goals is I wanted to know if, okay, so we could predict 2013 from 2012 scores, but is the prediction different for charter schools versus traditional public schools? Because there are some criticisms of charter schools that some of them, right, they're not all equal, and I need to, kind of stipulate that. But, some charter schools have been, criticized for teaching the test, right? Meaning they're just teaching test taking strategies and how to answer questions. And so if the test changes dramatically, right, it should impact them more than students who are taught the concepts. And so if the concepts are there, but the structure of the test changed, that should be okay. So this is kind of an interesting problem in that the residuals are something we can look at more than just diagnosing or checking our assumptions for our model fit. The residuals actually have meaning here if we look at it in terms of a grouping variable. So what I'm going to do here is I'm saving in the report card, I'm going to create a new column for the residuals and the residuals from the log model so I can look at both of them. And so first thing I'm going to do is look at the distribution of the two residuals. And we can see here that now realize the traditional public schools are much larger. I think it's probably like 96 or 97% of schools are non-charter. And so, of course, that's going to be the weight of the density, and that's kind of centered on 0. But the residuals for the charter schools is shifted to the left a little bit, meaning the residuals are a little bit more negative than what would be predicted from the model. Okay. We see the same thing if we use the log transformed distributions. Now, what's kind of nice is actually the residuals here are kind of normal. We got a little bit of a tail on the right side, but in terms of a model fit and kind of that assumption of the residuals being normally distributed is actually quite good, even though we had some skewness in our raw indicator variables. Probably a little bit better in the log transformation. All right. So now I can actually use the residuals and construct the null hypothesis test around the residuals. So my null hypothesis is that there's no difference in the residuals between charter and traditional public schools, right? Meaning the predictions are the same regardless of school type. All right. So if there is a difference in the residuals, well, that's because there's a difference in the prediction. And so one group performed differently than the other in terms of prediction, like either performed worse or better, depending on your point of view. And so here I can run just a student's t-test, where my dependent variable on the t-test is the residuals, and my independent variable is the charter school. So we could see here I'd get a t of 6.5, a p-value that's relatively small. Those are my means, a confidence interval that doesn't span 0. So what does this mean? So in this case, this means that charter schools in grade 8 math scored somewhere between 6 and 12 points worse than traditional public schools did, right? So we're saying the charter schools performed worse than what would be predicted from all schools. We see something similar. Now, again, this is where when we talk about the log of the residuals, now we're saying the log of the passing rate in 2013 is somewhere between 0.26 and 0.63. And we'd have to do some anti-logs to kind of figure out what that means, which is why I try to avoid it when I can. All right. So I want to show an example where we can actually use the residuals for something else that might be useful. Let's take any questions about that. Let me pause before I go on to the next bit. All right. The other thing I want to talk about, right? If we go back to that scatter plot, pointed out, doesn't quite look linear. Okay. So there's a couple of ways we can tackle this. One thing I do is lowest regression. I'll show that in a minute. But to my eye, right, it looks like it's just got kind of a curve, almost like a parabolic shape, right? So that would be called a quadratic model. So we've talked really about linear regression, but it becomes really easy to extend this to polynomial regression models. And we're still going to use the LM function, right? So what do we want to estimate? So we were estimating y equals, some beta x plus some intercept, right? So this is a slope. But what we want to do is add in this square term, right? Which is going to give us another coefficient, right? Which is fine, but we're still only have one independent variable. So in R, right? So I'm still predicting passing in 2013, okay? But I want to add in the passing of 2012 squared, right? So that I'm going to add that quadratic term. I have to use this I function parameter here. I can't remember you can look at the help documentation, but it's like the identity. This ensures that R does the squaring before the model estimation, right? Otherwise, if you leave it out, the LM function might do the squaring afterwards or in the wrong order. So that just ensures that that occurs that way. And so we get an R squared of 70.6% versus our 62% that we had in our original model, right? And let's, well, here's the full thing, but let's take a look at, I think it's nice to look at the model here, right? So the quadratic model I fit is this kind of curved line here, right? And think about it, right? The way the model is estimated is the same way. We're still trying to minimize the sum of squared residuals. All right. So the way to think about it is I need to take all of these points. I want these points to be as close to my regression line as possible on average, right, across the whole range. And so by allowing the regression line to bend, right, I'm allowing more points to get closer, right? Particularly all these points down here are getting closer. I don't have a lot. I have a couple of points that are kind of fall out further out. But overall, right, this should be a better fit than the linear regression that I have here, where I have a lot of points down here far away, some more points up here that are far away. If you run it, right, and I call the summary, which is, you're going to actually get multiple coefficients. So this is the slope and for the x term, and then this is the this, I guess you'd call it the slope for the x squared term. You're going to start to see, right, we have these null hypothesis tests here. We'll talk about this in greater detail next week when we talk about multiple regression, because in essence, we're doing a kind of multiple regression, or it's kind of stepping towards that. These, just so you're aware, this T statistic is, let's just look at this one. What this T statistic is from is the null hypothesis is that the estimate is 0. And so if you have a significant T statistic, that is indicating that this estimate is statistically significantly different than 0. Okay. A lot of times we just say that means the square term is a significant predictor of our dependent variable, right? And similarly for this one. And we'll see that again. We'll talk about that in a little bit more detail next week. And we have our R squared. And then the other kind of test we have, so we talked about ANOVA. So this, I want to just kind of justify a little bit why we spent so much time on null hypothesis testing, right? So again, we're going to do these regression models, and we're going to be doing a lot of little null hypothesis tests for each estimate. Now, in terms of ANOVA, we have this F statistic down here. What this is testing is whether or not all the estimates are different from 0, right? So in this case, it is, right? So we have a significant F statistic. So we have this model is significantly better than nothing to predicting our outcome of variables. One way you can interpret that, right? Now, I got caught last semester because a student asked, and I rarely look at this because in general, my P is always less than 0.05. In fact, it's almost always like so close to rounding to 0, right? Look at this. We got 16, we're going 16 decimal places out. Typically I know before I run a model whether or not it's going to be a significant predictor. Otherwise I wouldn't have bothered running the model or finding the data, right? So, but just so you know what's going on there. Occasionally you might.
Wait, I have a question.
Sure.
Just a quick one.
Yeah,
So
please.
for the models, do we lean towards the linear, or is it okay if like we see that like our regression line is like more quadratic, so we use like maybe a different like regression model? But Is it
Yeah.
that we like prefer linear?
No, you want to fit your
No?
data. You're going to try to fit your data as best as possible. In fact, here, let me go to the next slide. We can go crazy and do a cubic. Okay. And that would be, I guess, the maroon line is the cubic. Okay. You can see here, I added it, and so I increased the R squared to 71%. So maybe a percent or two, but here's my next slide. You got to be careful about overfitting, right? So cubic is ridiculous in this model, right? It is better technically, but it's almost, so there's sort of this balance. So if you see curvature in your data, yes, I think you should use a polynomial regression. But yeah, just be certain that that trend is there, because there's sort of this desire for what we call a parsimonious model. And what do I mean by parsimonious? So meaning I want the model to be as simple as possible that explains as much variance as as I can. So I think in this example, the quadratic is appropriate. It certainly adds complexity to the model, but I get enough benefit to offset the sort of little less parsimony I have in the model. Does that help answer your question?
Yeah, help answer my question a lot. Thanks.
Yeah. All right. So how do you know if you want to do a quadratic? Well, there's something called lowest regression that I like quite a lot. And this is often where how I come to the decision to do it. So lowest regression is a kind of like localized regression. And so if you're using ggplot, you can just add something called geom_smooth, right? And it will do, well, if you have less than 1,000 observations in your data frame, it will do a lowest regression. If you have more than 1,000, it does something called a GAM, which is just a slightly different way of estimating the parameters that's a little bit more efficient than lowest. You can always override it because there's a method parameter. So I almost always start with lowest because it's a little bit easier to understand, even though it's a little less performant with large n's. Okay, so how does lowest regression work? So this is a little Shiny app that I have in this visual stats package. If you go back and look and watch the video from last semester, I think I put a link somewhere of an introduction to Shiny. I actually gave a talk where I kind of built this Shiny app. So if you're interested in that, you can do that. So you got a couple of options of data sets. So I'm just going to do a quadratic, right? And the way, so there's a couple parameters. So what Lois is doing is we're going to start on the left-hand side. And it's going to try to estimate where the regression line is by using a weighted, doing a weighted regression of points around it. So over here, right? So here, these are all the points in the data set. The intensity of the green corresponds to the weight that's being used to estimate where that regression line should go at that particular point. So at -1, Lois is going to estimate it here because we're going to do a regression with these points that are up to white, that are filled, right? With these points contributing more than these points. So you can pass a weight into the LM function, right? And then it just takes the fitted value at -1. So I'm actually going to, I'm going to turn that on. So if I just turn this on, right, this little slider is just going to go from -1 to 1, and I can hit play. And so you can kind of see how the regression line is kind of drawing, right? So you see how the colors change as we move from left to right, right? So Lois is really great because it's going to try to take into account the natural kind of variation or the shape, right? And the nonlinearity of the data as you go from left to right. And here I can turn this on so you can always see what the full regression weight is. Now there's another parameter, right? So when you call it, I think the default is 0.3. So if I want to, let me pause it here, right? So if I'm here, right? but I want to include more points. So I can increase the span. Is it refreshing? Do I have to hit play again? It's not really doing anything on this one. Oh, right, because this is pretty quadratic. I'll show this in a moment. That's going to increase the points as you go, and you're going to kind of get overfitting. Let's look at a cubic function, right? So if I increase the span, I'll get if I decrease it, oh, I wonder if this is not working. I'm not seeing it change. Bummer. I broke it. I thought this was working. Well, span has to do with how far away from the point you're going to do. So you can see on a cubic, right, as we go from left to right, how it's kind of drawing those points. So anyways, to the other question, like how did I end up on quadratic? Well, I'll run a lowest regression, see what the natural kind of shape of it is, and kind of move from that. We can look at, this is Old Faithful data set. So we're looking at eruptions versus wait time, I think. And, you got to see. So here, I don't know what kind of polynomial model I would do. But anyways, you could play around with this and, kind of see different pieces. If you want to read about it, you can go to the about, or I think I put this link in the slides. We have a slight little write up on this to use. So lowest regression is kind of a useful thing to have. All right, go real quick. Now that we did that, if anybody's interested in these educational things, you can gonna bring this up. This will take just a second to download. All right. Here we go. So if you're interested in this, so this allows you now to look at that 2012 versus 2013. You can pick ELA in math, and you can pick any grade level. So, and then you can also look at means instead of passing. And then you can also switch between linear and quadratic fits. And then the model summaries are here if you change them as you go through. You can also look at the raw data if you're so interested. Now, and if you even want to go crazy, we can go and say, well, I want to just look at Albany County. So you can look at schools in a particular county and subset, run the models that way. So, and, the effects were greater for math than other subjects. But you could let's look at ELA grade 8 or something, right? So definitely more linear in the ELA world, but still relatively large R squares as we go through. Anyways, if you're interested in that, I think on the slide deck, if you just go to this repo, all the source code is here to create the app. So you're more than welcome to look at that. And then that kind of concludes, I think, linear regression. I think, let me look at the schedule because keep thinking there's a break. Okay, right. So we'll do multiple regression next week. And then we'll have a week off. And then we'll get logistic regression and Bayesian analysis. So we're really in the home stretch, even though we haven't had spring break yet, which is kind of crazy to me, but that's where we are. Questions about this?
Can I ask a question about
Yes.
Lab 8?
Yeah, sure.
Because apparently that's my role in class, is to ask questions about the labs.
I need to get I'll send you a certificate at the end for class question asker. It's great. I'm glad you're doing it.
Woohoo. So in exercise 6 on Lab 8,
All right, here.
One of the things that it asks is this an overestimate or an underestimate, and by how much?
Okay,
And
hold on.
it's not clear how to figure that out. So this is where you are trying to predict a country's personal freedom score with one that has a 6.7 rating of PF expression control.
Okay.
So how do you predict that? That part I got, but then whether or not it's over and under and how much, I wasn't sure how to do that.
So that's the question where you want to do so it's giving you a new data point, and
Yeah, it's saying if the rating, if the basically if the variable is at 6.7, what do you get for the personal freedom?
Yep.
And so how do you calculate that? Okay.
Yep.
And then it says, is that an over or under estimate, and by how much? And it was that second part of the question that I wasn't sure how to do.
Yeah, it should give you the actual observed value at that point. What's
well,
that?
there are no 6.7 values. That thing that was made it. Yeah,
Right.
they're only because they're going in quarter, so it's 6.75,
All right,
6.5. So
I gotta-
that's what made it a little bit tricky.
I got to refresh myself, so give me a moment. I'm trying to.
Right. I did notice that one, that there were no.
All right, let's just do this.
Exact
6.7
6.7. Yes, because all the values they went in quarter of a point, so they were like 6.25, 6.5, 6.75.
Right.
Yeah.
So we're.
Can I chime in what I did, Jason, and you can tell me
Yeah.
if it's wrong? I used the linear model that we'd already made, but then I made a fake data frame with just this one data point, 6.7, and ran just the predict function. So it's the old model on the old data, and then just the one. And then it's, for me, when I did that, I got 7.9. And then I ran another thing where I filtered some of the data. So I did something where I filtered it. There is no 6.7, that's exactly right, but I did anything between like 6.6 and 6.8. And that came out to that. Then there were a few data points, and then I just took the average of those. It was like 30 data points or something like that. And the average of those was 8.04. So I said it's a little bit of an underestimate, but that was my shot at it. I don't know if that's right.
Yeah, I did something similar, but then I noticed that if we looked at the M1, which had the fitted and residue values, then some of the fitted had a 6.70566. So then
Which
sure
which question in Lab 8?
using that.
I got myself lost.
6.
6 here. Oh, here it is. Here it is. Thank you.
So Noah,
I mean, but the only
what you're
way to
saying is
really
right, because I did something similar.
but really the only way to if you're overestimate or underestimate is by compared to the actual true value, right? So the ground truth, and since there is no ground truth at 6.7, you know, of course we can get the estimated value of our estimation. So what I did, I compared to the ones at 6.75 because those were the closest ones that I had. So I thought that was the closest ground truth that I had for comparison of how my model was overestimating or underestimating. I mean, that's what I did.
Yeah, I think that's fair. I think they're I've heard Noah give. I think both are appropriate ways of trying to estimate that.
And the result comes out very similar to what Noah did because.
Yep. Yeah. I think as long as you explain, right? So this the point of this question. Now I got oriented. So, sorry about that. I have to remember this stuff. Because is. This looks pretty good. So you're going to be close and you could probably justify either way, but you guys done the actual calculations. But let's go to where's the original? no, I want the one with the regression line. I think you might see it a little bit more here. Well, I guess I leave this one. So if I look at this scatter plot, right, and I said, well, what's the predicted value if you had, what is this, 85 or something, right? I would predict this. That would probably be an underestimate based upon the raw data because all the points are well above it here, right? In this case, right, so you just want to look at the ones close. So if what was the value? 6.5, is it? So we got it's probably somewhere around here. So if it was here, I mean, geez, there's more points below than above. So you might say it's an overestimate. I probably here it might be an overestimate, but then if you were up here, it would be an underestimate. So part of the issue is this as a regression model is not terrible in the real world, but there are some homoelasticity issues here, meaning you don't have constant variance around the regression line, right? So look up here, we have almost no points below, right? And then we suddenly shift where we have more below, and then I don't know what's going on here, right? So it's kind of tightly above, and then we got some stragglers down here, right? And if I plot the residuals, I'd probably see that a little bit more clearly. So you're going to have some variation as you move from left to right across your regression model. So as long as you explain how you got to it. So I think, Juan, you said you just took the closest values and looked at the average, since we kind of have a discrete dependent variable. Fine. I think, Noah, you took some around in both and took the average. That's fine too. So yeah, but just explain what you're doing and why you're doing it. And the point being, so I'm glad you brought this up. The point being is we don't have really great, there's some violation of the homoelasticity assumption here. And that's what we're getting at. If you had that, it was like perfect balance all the way across, then it should just be good. Just be good. I don't know if I can, so we're looking at, do we have, oh, it's a Tibble. Of course it's a Tibble. Did I calculate the residuals here? All right. Let's look at this. So if I do LM out, so we're going to do LM. So that's the dependent variable. What was the PF score?
I think M1 has the residuals and the fitted values. Is that what you're looking for?
Oh, maybe. Well, that's a list. What is? Oh, that, yeah. I just calculated again. So, yeah, so you can do predict LM out new data. So this is something as a data science you probably do a lot. So we'll say data frame. 6.7. Right, so we would get new Y, I call it, I guess. Right, so let's, where did I do this plot? Is it this one? Oh, by the way, right, we're using the smooth here. If I change this to Loess, you can see a little bit of bend, right? There, but we'll put it back to LM, because what I want to do is now do geom point x equals 6.7, y equals new y, color equals red, just to make it stand out, I hope. All right, so that's the point where, so we can even size equals 3. That's kind of where we're focusing. So yeah, I know Juan's strategy of doing that. Yeah. So either of those strategies, I think, kind of work. But yeah, let's look at since we're here. So we could say HFI predicted equals predict LM out. Oops. Why did it do that? Oh, probably because I lost. There's some missing values. So complete cases, HFI. But I really only want to look at PF score. Sorry, I'm doing this the old school R way because I'm still faster that way. I need a comma, I think. So if I do that, get that. Okay, now that works fine. So then I could say HFI residual is HFI PF score minus HFI predicted. Oops, what did I do? Okay, now I can say ggplot HFI AS X equals should be the same PF expression control Y equals residual geom point. So I probably will add geom H line Y intercept equals 0. Okay, so here you can really see it. You can kind of see that the variant, you don't have equal spread as you go from left to right. It almost looks like it comes to a cone to a point over here too. So there's kind of a number of issues, subtle, but in this data set, but they're there. Anybody, do you want me to throw this R code in the chat? Good question. Any other questions? All right, so now I need to know. So you guys are learning tidyverse. So let me rerun this so I can get HFI back to where I want. So probably the better way to do this is HFI piped to, we could probably do select PF score, PF expression, and pipe to, oh, what is it? Someone tell me, what is it? Is it, it's not complete cases in dplyr. What is, no, it's unique or distinct. Is that what it is? I'm trying to remember all these words. I think that was it. Distinct. Oh no, distinct probably, no, that's not what it is. I would have got rid of duplicate. No, missing. Missing. All right, I got to go to Google. dplyr missing rows. It is. Angela, can you help me?
I'm not sure what you're doing.
I wanna replace this with dplyr. How do I do that in dplyr?
Oh, no.
The assignment for the students.
Oh well. Yeah, I guess I could run it through summarize first.
Are you sure it's not distinct?
No, distinct is equivalent to the
Unique.
duplicated.
Yeah, it gets rid of everything
Yeah.
that's not unique.
Could you filter?
Yeah, I guess it would be in the filter, right?
What are you trying to do? Are you trying to do a group by?
No. I just want to remove rows that have some missingness.
Oh.
Oh, could it be any more obvious? Oh no, that didn't work. That's what Google told me. Oh, that's in tidyr. It's not full join.
So east.na is not a. Is that what you're looking for? Trying to filter for those out?
Oh no. The is NA just gives you returns true or false of whether it's not. I mean, sure, I could do this. I could say then mutate. Oh, I guess no. I could say filter. Yeah, you're right.
Yeah, filter. Yeah,
It
not this. Yeah,
NA PF score and not is.
yep.
I feel like there's a
A neat way to do it.
a neat way to do it.
Yeah.
Yeah. Wow.
Yeah, that works.
That works. That works. Yeah, I don't mind that.
All
I
right.
don't know. I'm trying. See, I want everyone to know I'm trying to learn too. I'm trying to learn. I'm trying to use the dplyr tidyverse way of doing things instead of. But I've been doing this for 15 years, so it's hard.
That's fine. At 9:07 p.m., I'll take that answer.
Okay. Any other questions? I'm sorry, you guys are just watching me. You could drop off now on. I don't know if this is helpful or not.
Do you discourage using tidy models for the project?
No, go. You can go for it. It is still very new. In fact, I'm looking forward. I'm going to the RStudio conference this summer, and one of the major things I'm hoping to get is some updates on where they are on the tidy models. I saw Max Kuhn and I'm not sure who else are getting close. I think pre-orders for their book on tidy models is coming up. I think it's going to come out this summer. So absolutely, if you want to start to learn it, it's definitely the way to go. If you, it's kind of a replacement for the carrot package. I don't know if anybody's encountered the carrot package. Definitely the way to go because it unifies the interface to all the different predictive modeling interface. You know, is we'll see when we talk about logistic regression in a few weeks. When you start the predict function, you always use call predict, but depending on the model type, you get different results. And that can be problematic. So tidy models would be a good way to go.
I put the link in the group chat if anyone's curious.
Yeah, they're doing some pretty neat work. One of the cool things about dplyr, and I think this may extend to tidy models, is dplyr will write SQL code for you on the back end. So you can use dplyr to do your data munging, but actually have it execute in the database. All right. So if you're in a production environment, right, you can use R to do the data munging, but all that SQL code is generated automatically for you, which is really cool. So I think the hope with tidy models is, and then there's a whole class, like there's something called recipes, which is your data setup stuff, that a lot of that stuff you can eventually offload into a database if you wanted, which is pretty slick. All right, I'm gonna stop recording. Have a good night, everyone. Sorry for the digression. We'll see you next week.
Thank you.
Thank you.